Optimization problems. Yes, your favorite problems from Calculus 1. Remember those? Yep. Finding the max and the min for a situation, for in science, in geometry, in economics, find maximizing the profit, minimizing the cost. What else? Finding the maximum of a rock, or the maximum height of a rocket given the function. So yes, it was kind of a drag to solve those kind of problems, especially when the situation requires some knowledge in geometry and many many other not just the differentiation rules. I mean, also because when you differentiate the function, set it equal to zero to get the what you call the critical values. Solving those equations could be a challenge. Well, now imagine these problems with two variables. Okay. So, well, that's going to follow essentially the same process as we did with the plain problems. That is, without any context related, which were the functions just given. But in this case, somehow they're going to tell us that we're going to have a minimum or a maximum, right? And well, the guidelines to go through these problems are essentially the same. So if possible, draw a picture to represent the context of the situation, labeling any variables that you think could be relevant to then come up with a basic model that we can use to do the calculus on. All right, and yes, that's the next part essentially. Write a function for the quantity that is to be optimized, that is minimized or maximized, and then so that is going to be our primary equation. Recall from Calc 1 when you're solving optimization problems, you have a primary equation and a secondary equation. The primary equation, it's the one we do the calculus on, the derivative, the set equal to zero, etc., etc. And the secondary equation, it's the given information or a constraint typically, and we use that secondary equation because on the primary equation we started with a function of two variables, and well, back then you didn't know anything about functions of multiple variables. I mean, yeah. So we use that secondary equation or that secondary information to get rid of one of the variables and work with a function of a single variable. It's going to be the same thing here, except that we will start with a function of three variables. We're going to use our secondary equation to turn that function into a two-variable function. All right? Okay, so what else? Find the critical points and then evaluate each to determine max and min. The rest of the problem, it's the same. Well, the same spirit of the problem from Calc 1 and what we did last time. Okay, let's do one example. Okay, so our company is designing a rectangular box with no top, all right? No top and a partition down the middle. The box must have a volume of 48 cubic inches. And they're asking us to find the dimensions of the box that will minimize the amount of material, right? So that is, well, you typically minimize the amount of material. It could be a little tricky. Maximizing the volume, well, that's easy. You just work with a volume function. But when it comes to minimizing or in general amount of material, what does we mean by amount of material? Well, that's in this case related to the surface area of the box. Okay. Well, let's draw a picture, of course. That's going to help us a lot. So number one. So we're going to draw a box right here, a rectangular box that looks like this, right? And with a partition down in the middle. So that's going to look like this. Right? So that's our box right here. Right? And keep in mind that there is no top on the box. Okay? How about we label the sides or the dimensions of the rectangular box? Well, it's a three-dimensional box, of course. So how about label this as our x y, and z. Okay, so so here in this case, they're asking to minimize the amount of material. That is, we're going to minimize the surface area. Well, so in this case, we need to analyze this box to find how many parts would be comprising this box. Okay, so number one. So let's write it down in let's write down in words. So SA, surface area. Okay, so let's have a look at this box. That means we have one bottom, right? Bottom. What else do we have? So we have one front and one back. Okay. What about the sides? How many sides do we have? Really? 3 sides, right? So the left, the right, and the one in the middle. So plus 3 sides. Okay. With this, we're good to go and write our primary equation, our objective function, the one we're going to do the calculus on, the one we're going to get max or min, in this case the min. Okay? So the objective function, okay, let me label it as an objective function. Objective function, well, so that'll be f of x, y, z equals, okay, so let me talk about the sides, the 3 sides, okay. Do you see how the sides involve y times z? Alright, so because we have 3 of them, that is 3yz, okay. What about the front which is xz plus the back, which is another xz, and what else do we have? The bottom, right? The bottom, which is xy. Okay, so let me label them again. So sides, front, back, bottom, right? But we have a problem here. We have 3 variables, and well, we didn't learn about finding max and mins for a function of 3 variables. So the d-test is only useful for functions of 2 variables. Of course, we could extend this idea to 3, 4, 5, 17 variables. However, we need a different way to solve this problem, and rather than using the d-test, we need to learn about the Hessian matrix, which it's going to be a pain. Well, this class should be a 5-unit course, so we can go through those extensions. But well, we're not going to go that way. That's why we're going to use the secondary equation. What is that secondary equation? I'm going to label that as number 2. Or secondary function. So that is the given information. Well, what are we given anyway? Are we not given that the volume is to be 48 cubic inches? Well, so volume, that means volume equals to 48. But how do we get the volume of a rectangular box? Isn't that just the product of the 3 length times width, in this case x, y, z? So that is x, y, z equals to 48. All right. What did we do back in Calculus 1? So in Calculus 1, we had a function of x and y. We used our secondary function to solve for y to get everything in terms of x. Okay? So that means, in this case, I'm going to solve for z for this equation to leave everything in terms of x and y, to have a function of 2 variables x and y, and repeat the process that we did last time with a function of 2 variables x and y. All right? Let's go about that. So let's solve for z. Number 1, 48 divided by xy. And I'm going to replace every instance of z in our objective function with the quantity 48xy. Okay? Actually, I'm going to combine like terms first of all. So now I'm going to have f of xy equals 3yz, which is 48, over xy, xz plus xc, that is 2 times xz, which by the way is 48, over xy. And lastly, plus xy, that's just xy. We don't do any substitution there. So that's good. We're good to go. Let's simplify this function as much as we can and also write it in a way that we can do calculus on it. All right, so that means f of xy equals, I'm going to reduce the y's right here, and so reduce the y's and reduce the x's here. That's going to leave us with 3 times 48, which is 144, over x, which is the same as saying x to the negative 1, and 48 times 2, that equals to 96. See how we reduce the x's, so we're left with y in the denominator, move it to the numerator with negative exponent, plus xy. Right? So that is the function that it's ready to do calculus on. Alright, let's find the two partial derivatives, set them equal to 0 to solve the system of equations. That will give us the point or points, the critical points. Alright? So, and in this case, I think it's going to be only one because, I mean, it's a geometry problem. I can already tell it's going to be only one. Okay, so partial derivative with respect x. So negative 144, x to the negative 2, what's that? Plus y. Because it's going to go to 0, the derivative of x is 1 times the coefficient y, it's just y. So that's the partial with respect x. Let's get the partial with respect y in a similar way. That equals 0, negative 96, y to the negative 2, plus x, because the derivative of y is 1 times the coefficient x, it's just going to be x. That's the only term that survives the differentiation. Alright? Oh yes, a system of equations with negative exponents. That's another nonlinear system like the one we solved yesterday. Alright, so that's going to be an interesting one. Alright, so from here, how about, okay, so how about we solve for y? Y equals negative, or actually positive, 144, x to the negative 2, which is the same as saying 144 over x squared, right? So now that let's forget about the calculus part of the problem. Let's focus on solving the system of equations. So, yes, I just solved for y over there in terms of x. So I can substitute it in the second equation and get the x values here. All right? Okay. So that'll be, okay, over here, that's going to be x equals to negative 96, y to the negative 2, which is the same as saying x, positive, not negative, positive 96 over y squared. Okay? So, what do you say we substitute this y over here, and don't forget to square this. Okay? All right. So this will be x equals to 96 divided by quantity squared, which is 144 over x squared. All right? I know that looks like it's going to be a nightmare with the numbers. I know 144 is going to be a huge number. Don't square it. Leave it as 144 squared. Okay? You'll see how it's going to work later. Alright, so number one, I also need to, okay, well, let's square first. X equals to 96 over, parentheses, 144 squared, x squared squared, x to the 4th power. So, again, dividing by a fraction, it's the same as multiplying by the reciprocal, which is going to look nicer if we do the following. X equals to 96 over 144 squared times x to the 4th power. All right, so we are in a situation that it's similar to the one we ran into yesterday's problem. So how do we solve this equation? Yes.
Move the x to the right hand side.
Why would we do that?
So we could like factor out the x.
And then, so why not dividing out both sides by x? Guess what? In this case, it's okay to do it. I know, it's weird, right? Because, so, are we in trouble if we divide by x here? Yes, the solution can potentially be 0, I agree. But think about the context of the situation. Are you going to have a box whose length is equal to 0? So x is never equal to 0, so no problem here. Just divide it, all right? In this case, it's okay because there is a physical context tied to it. Not like last example in which we didn't know any context about it. Then we have a problem dividing both sides by 0, right? Okay, so in this case, that's a 96 over 144 squared x cubed. That is equal to 1. And let's solve this baby cubic equation. All right, so let me solve for x cubed equals to 144 squared over 96. And then x equals plus minus the cube root of 144 squared over 96. So, which in this case will be a nice number, plus minus 6. Do we agree with these answers? Let's have a look at it. Do we agree? Well, only positive 6, right? Yeah. So do we need plus or minus when the index is odd? No. Even if we had an even index, well, because we are looking at a physical problem, the negative wouldn't make sense. Okay? So then in that case, you would need to write a note. Oh, yes, it's an even index, a radical, but we disregard the negative because it's a physical problem. All right, well, we already have x, that's the length. How about we get y, the width? So we already have an equation to find the width, that is 144 over 6 squared, which is 144, over 36, which equals to 4. All right? Equals 4. Okay, that's the second one. And now that we have x and y, how about we go back to almost the very beginning of the problem where we stated the secondary function. We have an expression, so one equation solved for z. We can use it to find the value of z. Z equals to 48 over x, which is 6 times 4, that is 48 over 24, which equals to 2. All right, and those are the dimensions. That is, dimensions are they in cubic? Are they in inches? Yes. So that is 6 by what's that? By 4 by 2. All right. Multiply those three numbers. 6 times 4, 24, times 2, 48. That gives us the volume we are expected to have in the box, right? So, did you see the pattern? See how it is basically the same as the problem you solved in Calculus 1? Objective function, secondary function to get rid of one of the variables. Calculus, find critical points in this case, not just critical values, but critical points in this case. And then once you get those critical points, just backtrack to the very beginning, to the secondary substitution, and to the very beginning secondary function to get the unknowns. All right, in this case, the dimensions that will maximize that will give us the minimum amount of material in the box. Constrained to 48 to have the box to hold 48 cubic inches. All right. Okay, like I mentioned before, I'm going to skip the next problem, but I think I have a recording where I have this problem solved. I'll let you know where is this. So I really want to get into Lagrange multipliers today. Let's do one more problem. This one is going to be very short. Okay. A flat metal plate is located on a coordinate plane. The temperature of the plate in degrees Fahrenheit at the point xy, that is, the temperature distribution, is given by this function here. All right, so, okay. Find the minimum temperature and where it occurs, right? Because again, this function tells us that the plate does not have, the plate's temperature is not distributed evenly. And that's because whatever the material it's made of, it's not a uniform material. Even if it's an alloy, it may not be uniformly made of it, all right? So that's why the temperature might be different at different points. Okay, so let's do the calculus. Let's get the calculus. That is, so the partial with respect x and the partial with respect y, that is 2x minus 8, set it equal to 0, and 4y plus 4, set it equal to 0. Solving the system of equations, that's going to give us 2x minus, or let me just go here. So 2x minus 8 equals 0, and 4y plus 4 equals 0. Okay. So solving the two equations, very baby equations. So that is x equals to 4 and 4y equals to negative 4, y equals to negative 1. So that is our only critical point in this case. That means that's the point where the temperature is the minimum. Where is the coldest, if you will? All right? And where is it? Yes, at this point. Now, let's see. Let's show that this is a relative minimum still. So that is t sub x, double x rather, that is 2, t double y, that equals to 4, and txy, that equals, okay, x with respect to y, that's 0. Right, let's recall our quantity d to find whether it's a REL max or a REL min. So d, which is t double x, t double y, minus txy, quantity squared. Okay, so that equals, okay, 2 times 4 minus 0 squared, which equals to 8. Well, in this case, d happens to be positive. And what is the sign of t double x? Isn't it also positive? That's the second derivative to be positive, which means concave up. That means we have a relative minimum. Okay, so t double x is greater than 0 and d is greater than 0. Therefore, we have a REL min. All right, so we have a relative minimum. Now, there's a part B to that question. A second part to that question. Is there a maximum temperature? What do you think about this one? To begin with, we don't have another critical point that we can analyze for max or min using the D test, right? But let's think of the physical context of the situation, and then also think about, look at the given function, look at the behavior of the given function, about how it works. So there seems to be a maximum there. Looks a hell of a lot like paraboloid, right? Yeah. Which is just going up and up and up. Well, there could be potentially a maximum temperature. That's going to depend on the capacity of the metal plate, of the material that it's made. So infinite temperature, not really, all right? But still, you can just increase as much as the material can endure in this case. Okay, part B of the problem. What is the value of the gradient at the point you found in part A? What does that mean anyway? So here's where we are going to make a pretty cool connection. That is nabla of t, which is the partial with respect x, comma, the partial with respect y. That is, okay, well, didn't we get the derivatives already? That's 2x minus 8 and 4y plus 4. So, they're asking us to evaluate the gradient at the point, what was that? 4 comma negative 1, right? So substitute, what are we going to get? 2 times 4 minus 8, 4 times the negative 1 plus 4. What do we get? Don't we get the 0 vector? So here is where we can relate the idea of finding a maximum and a minimum value. So in the end, when we're solving a max and min problem, we are finding the vector at which the gradient equals the 0 vector. I mean the point at which the gradient equals the 0 vector, because we're setting the partial derivative equals with respect x equals to 0, the partial with respect y equals to 0. Hey, so that's how we can relate max and min with the gradient. All right? Okay, so I believe this is going to be the end of hold on, the maximum value. Oh, of course, the maximum value at this point, that is simply the square root of 0 squared plus 0 squared. Oh, come on, that's going to give us 0, right? So that's where there's no change, essentially, right? So in relation to what we learned in Calc 1, those are the points where the tangent line equals 0, no rise over run, right? There's no change at all. Here is where the gradient is not changing at all. The magnitude of that vector that describes the change in the direction of x and in the direction of y, it's equal to 0. Okay, let's talk about 18.5. I mean 15.8. That is actually the last section for this chapter before we get to chapter 16. Okay, so if you were not here last time, I still have a few extras for these notes. Okay. All right, so let's talk about